know how many floral buds you start with before you prune, and you have to end up knowing how many fruits you end up with, and you have to know what the target is. So let me break it down a little more with what are the specific things we need in each one of these specific parts. Let me start first with precision pruning. Now, in precision pruning, we need from you companies the ability to count buds before pruning with computer vision. Now, buds are small. This is not the easiest task, and so few have attempted it, but nevertheless, it's one of the essential parts of this whole process. Now, I realize, and all of you in the working in this space know it too, that there's always occluded buds, and later on there's occluded flowers, occluded fruitlets, and you're not going to see everything with computer vision. And buds are small, and then some of them are not floral, and the ability to distinguish a floral bud from a vegetative bud is not something we've been able to achieve yet. And so there will be the necessity of having a correction factor on each one of these things that we need done. But having said that, if we can count buds before pruning, then we need to calculate what is the target that we want. Now, this is a part where I want to spend a few minutes talking about the issues in trying to decide how many buds you want on that tree before you prune it. Now, in green, I indicate that you can use as a denominator. If you know the number of buds on the tree, to normalize it for tree size, you can use the trunk cross-sectional area. That's the traditional method, and I'll show you something about that and say why it's also not the best. You could possibly measure the total length of all the branches on the tree with computer vision and use that as a denominator. You could measure the diameter of each of the branches on the tree and calculate their branch cross-sectional area and use that as a denominator, or you could use canopy volume. Now, the best method I didn't list here is to measure leaf area and use total leaf area as a denominator, but I didn't put that down for a couple of reasons. But before I explain those points in green, the next step in making this useful is somehow being able to communicate what the target is to the human worker in some sort of actionable information and in real time. So if you could do that and guide the human worker to prune according to what is the optimum bud load for each tree in the orchard, then we could get closer to precision pruning. And then once we're done with that, we want to count again using computer vision to determine how close we came to the target with the human pruning. Now, let me focus just a little bit on these methods of counting. We've done a couple of trials, and I'm presenting one here that we did this year with Gala in 2023, where we looked at in several locations around the US. This shows data only from New York and Washington. On the x-axis is the number of flower clusters we left after we pruned. So on the right-hand side, you see some trees had about 330 flower clusters. Those trees received a very light or minimal pruning. And if you move towards the left on the x-axis, you come down to somewhere less than 100 flower clusters. Those trees received quite a severe pruning. Now, the interesting thing is that just pruning alone has an influence on the final number of fruits you end up with. So on the y-axis is the final crop load. Now, these trees, after they were pruned, received a full normal program of chemical thinning that was based on the local person's strategy. And so in Washington, they thinned a certain way, we thinned a certain way in New York. So we put on a bloom spray, 2 bloom sprays, a petal fall spray, and a 10-millimeter spray, but the trees didn't receive any hand thinning. So this is just a crop load that you've got after the final chemical thinning with these different levels of pruning. And you can see that from the red line and the purple line, that more pruning give you a smaller crop load at the end. Now, we estimated that these trees should have somewhere around 150 fruits, so that in New York, we should have pruned somewhere closer to 150 flower buds to get that. And a tree that had no pruning or minimal pruning would have had way more than that. It would have had a crop load of around 20. so that it illustrates the need for precision pruning. If growers don't prune in a correct manner with the proper pruning for the crop or for the tree size, they often end up with too many fruits, even after chemical thinning. Now, they can solve that with hand thinning, which is expensive, but this creates the problem. Now, if we look at the corollary to that, the same different levels of pruning resulted in different final fruit sizes because of the different crop loads. And you can see that when we prune very lightly, fruit size in New York was under 100 grams. Those are really small galas. In Washington, they can generally produce a larger gala at any given crop load, but still at both locations, to get the proper fruit size, you had to prune a certain amount. Now, that exact amount is what we're after with precision crop load management. Now, I want to switch to the issue of how to calculate this optimum number. So we need some way to normalize the trees. Now, if you use trunk cross-sectional area, we can measure trunk diameter with computer vision. And in fact, we worked with one company that will use their cameras to go up and down the row and give us trunk diameter measurements. We can convert to trunk cross-sectional area without problems. The real issue comes in the second point. The trunk cross-sectional area really is valid on young trees up to year 8. But thereafter, each year, the trunk cross-sectional area increases each year, but the number of fruits per tree tends to plateau. And so that we can't give a consistent ratio of fruits per trunk cross-sectional area that's valid over the whole 20 or 25-year life of an orchard. However, we do think we can mathematically adjust the crop load after year 8 based on TCA, based upon a lot of data that we have of the way trees grow and their trunk increase every year. So that's not a method that I want to reject, but I do realize its limitations. Now, second method is to, with computer vision, measure the diameter of all the branches on the tree, add them up, and get a total branch cross-sectional area. Now, this is very attractive because usually all the branches on the typical tall spindle tree, which is mostly what I deal with, they're not in there on the tree for long periods of time. We tend to renew any branch that gets relatively dominant, and so they're usually cut off the tree before they get older than 8 years of age, when branch cross-sectional area wouldn't be that useful. And since we can continually renew branches, and the tree, even though it might be 15 years old, has small branches, the total branch cross-sectional area would be a useful method. And so that's another thing that companies could think about measuring to give us the right denominator. An alternative would be using computer vision to measure the length of all the branches on the tree and use that as a denominator. Or lastly, using computer vision, measure the canopy volume for 3D canopies, or even canopy area for 2D canopies, and come up with a number of fruits per cubic meter of canopy or square meter on a two-dimensional canopy. I would like the companies to think about how in their products they are going to help us with one of these methods calculate the proper crop load or the target that we want. Now, we did this study with a company to look at measuring trunk cross-sectional area this year. We did 4 varieties. And these graphs show the manual measurements of trunk cross-sectional area versus the computer vision calculation of it. And you can see that in all cases, the computer vision system was slightly different than the manual system. So with the manual system, where we would say measure 50 square centimeters here on Gala 1, the computer vision was measuring 35. And the slopes were not exactly parallel. This would require either better ways to measure trunk diameter or a correction factor. So if I want to summarize this part of the presentation on pruning, it's a space that not many of you companies have worked in. We think it's essential to be able to count buds. We are willing and accepting that there will be a correction factor on those counts. But the point I want to make here is we believe that each tree has to be georeferenced if you're going to then allow the human pruner or a robotic pruner in the future to prune the tree to its proper bud load. And so georeferencing each tree becomes important. Some companies do not give individual data per tree, but on sections of row. I'm going to try to make the case as we go through this that georeferencing each tree is the ultimate way to go, and we should all work towards it. And then the other blue point is once we have a target, we somehow have to communicate to the human worker specific instruction using the georeference for each tree for each individual tree. Let me give some examples of why I think georeferencing each tree is essential. Now, some of you have not bought into this concept. Some growers think it's an overkill, but all the time I've been working on this, my ultimate goal was to do a precision management on each tree. So this is a row of trees here at Geneva, in which we scanned it to measure flower buds before pruning. And the yellow line shows the differences in the number of flower or buds that we counted on each tree with a correction factor. Some trees had a huge number of buds, in this case, close to 800 and 800. Others had much lower numbers, closer to 400. The black line is the target that we calculated for each tree based on trunk cross-sectional area. And you can see that all of the trees had more buds than the target, with the exception of this one tree, about tree 32, which started the season with slightly fewer buds than the target. So the goal in pruning would be to reduce this height of the yellow line to exactly the black line. But my point is the black line is very variable when you go down the row. Some trees are bigger, some are smaller. Some of this is due to variability in the soil, giving different tree growths as we go down the row. Some is due to the issue we have in the US and many places in the world of tree death due to fire blight. And so we sometimes have replacement trees in there, and nevertheless, there is variability down the row. Now, we've looked at this at a couple of places, and I just published a paper saying that maybe this variability doesn't exist in all orchards. Certainly some very, very uniform orchards might not have this, but if you want a robust system in your product, you're going to have to be able to account for this variability in each tree down the row and give data based on each tree, which would be georeferenced. Once we have that information, my concept on how this can be communicated to an orchard worker on a platform was simply using some sort of an iPad. Now, I can envision a platform having an RTK GPS sensor on it, and then this iPad mounted in front of the pruner with an arrow pointing to the tree that he's looking straight at, and it has a simple instruction: remove 3 branches from that tree. And the tree coming up just to the left, it already has an arrow indicating how he should prune that, and it has an arrow to the right showing the tree that's just passed, how he should have pruned that. And as it goes down the row with the RTK sensor on the platform, it can sense which tree, and then just a simple lookup with a map that's loaded into the iPad to look up what that tree should receive. And all the processing about how many branches to remove, or it could be buds to remove, would all be done preloading onto this iPad. Now I'd like to move to the second aspect of precision crop load management, which is the chemical thinning period, which starts at bloom and goes till fruits are about 20 millimeters. It's a more complex scheme. It starts with assessing the initial flower load on the tree near flowering, could be right before flowering at pink, and then applying blossom thinning sprays guided by the pollen tube growth model that Greg Peck is working on and Tori Smith to simplify. Following that, applying a chemical thinning spray post-bloom. We call it, the first one is the petal fall spray. But then very essential to this process is being able to assess the results of these first sprays, the two bloom thinning sprays and the petal fall spray, using the fruit growth rate model. And this is where we need help from companies to be able to implement this fruit growth rate model using digital technology, not manual measurements that we currently use. And if that model indicates we still need more thinning, apply another spray when fruits are about 12 millimeters, assess the results using the fruit growth rate model, and if needed, a final spray at 16 to 18 millimeters, and then assess the results with the fruit growth rate model, or count the number of fruits at the end. So it starts with trying to count with computer vision the flower clusters at pink, and then maybe every day after that. The second reason for counting every day is to determine when the tree has enough flowers open to launch the pollen tube growth model, which is based on temperature, but it has to have a start point. Then that will define for the grower when they apply the first blossom thinning spray and then the second blossom thinning spray. It would be wonderful if we could use the orchard map with each tree georeferenced of blossom density to then program a smart sprayer for bloom thinning and spray more where there is more flowers and less where there's less flowers. Some of you are working on that, particularly Aria, that I'm aware of, and so that becomes an essential part of this. Then as we go to the petal fall spray, we would also use a smart sprayer to apply more chemical where needed. But then we would need to assess the results of those first bloom sprays and petal fall spray using some method to run the fruit growth rate model using computer vision. Now, for those of you not familiar with the fruit growth rate model, it's a model that estimates fruit growth rate over a 4 or 5 day period. Usually 3 or 4 days after spraying, you start and you measure diameters of fruits. You measure them again 7 or 8 days after spraying. And the difference in their growth can be used to determine which fruits will fall off and which will persist. We do this now by measuring their diameters physically with a caliper. It would be so much better to have some method of computer vision to measure diameter. Now, the challenge is this has to start when fruits are 7 or 8 millimeters, and that's really difficult to measure their diameters. And then would have to be remeasured when they're 10, 11, 12 millimeters. And then after that, you can measure again, but fruit sizes are larger and it may be not so difficult. But we need computer vision to measure diameters of fruitlets between 5 and 20 millimeters. And then we would want to reutilize computer vision and the fruit growth rate model after each spray. But at the end of this process, we would then want to count fruitlet numbers when all chemical thinning is done. Now back to smart sprayers. I really would hope that we could work with different companies or all of you to have data that you would produce with computer vision of counting flowers and then fruitlets to guide a smart sprayer. Now, this is one of the areas that I feel is a little bit of a weak spot for us horticulturists. I don't know of good data showing that differentially spraying certain blossoms on the tree and others not, or particularly with the hormone thinners at petal fall and onward, will give the horticultural result that we want. Up until now, most horticulturists believe that the hormone thinners, their result is based on the total dose for the whole tree, not just on the individual cluster. But a smart sprayer would spray maybe the top of the tree differently than the bottom of the tree, or maybe even individual nozzles on that smart sprayer would spray certain portions of the cluster branch with a spray and others not. We need to cooperate with those trying to do the smart sprayer concept to measure the final result with solid horticultural studies showing that we are getting the right amount of thinning if we don't spray the whole tree. And that smart sprayer would be essential to us at the later sprays as well as the earlier sprays. So let me just show a little bit of data that we did this year or the last few years of counting flower clusters and how the computer counts, computer vision counts, correlate with manual cluster counts. And so we have 3 varieties. The diagonal small black line is the 1-to-1 ratio. And you can see that with Fuji, if flower cluster numbers were essentially below 200, we were pretty close. But when we got very high flower cluster numbers over 200, then we were typically underestimating the number of flower clusters with these computer vision counts. With the second one, Gala, we were very, very close with the manual counts. And in the New York one and Gala, in the last slide at a different location, we were fairly close with the Gala flower counts, but the New York one, for some reason, we were underestimating the number of flower clusters using computer vision. But this is an essential part that all of the products, if you're trying to sell to growers, I think we need this for them to be able to have good estimates of flower number to calculate the target fruit that they want at the end. This is a little graph showing that with one system that I'm aware of at the moment, which is the Pometa system based with the cell phone, in using the fruit growth rate model. Here we did the fruit growth rate model with manual measurements, and that's the blue dots called MaluSim. And we estimated fruit growth rate with the Pometa cell phone system and estimated fruit drop. This would be in early June. And then we harvested the fruits at harvest in September. And this showed how well we predicted the final fruit number with either the MaluSim model or with the Pometa computer vision system. And the results were really impressive. We were very good at estimating how many fruits were on the tree as early as the first week of June using the Pometa system or the MaluSim fruit growth rate model system. It was interesting that as we got to greater and greater fruit numbers, above, say, 250, when we had 300, 400 fruits per tree, our estimates were not so close to the true value. And we think that's because with high fruit numbers, you can tend to have some fruit drop in what we call June drop, which these counts were made before June drop in late May and early June, so that we could not account for June drop with those estimates using this cell phone Pometa system. But this system, or the ability to count and measure diameter of fruits to run the fruit growth rate model with computer vision, is essential. Now I'd like to move to the last part of this, and that's just our concept of how precision hand thinning would work. We would hope that the hand thinning, which begins typically in the Northern Hemisphere, middle June to late June, we would be able to go through with computer vision system and count the number of fruitlets before hand thinning, georeference each tree, and have some method of estimating the trunk cross-sectional area or the branch or whatever from an earlier scan in the dormant season, and then calculate the target number of fruits for each tree using the appropriate denominator, and then communicate that information to each worker for each tree to guide their hand thinning. And then after we're done, go back through with computer vision and count how many fruits we ended up with to make sure that we accomplished our objective. So we did this in a couple of places. I'm just going to show one data. We did this in Geneva, and we did it at the Hudson Valley, cooperating with Jared Buono last year. This is a Geneva data. The gold colored line shows the number of fruits that we ended up with after chemical thinning in this particular row of 97 trees. The black line is the number of fruits that the tree should have had to have its optimum crop load. And so when you compare the gold to the black line, there are several trees that still have more fruit than they should have, but there's also some trees that have way fewer fruits than they should have had. And this is a consequence of chemically thinning everything uniformly. Now, maybe on average, we ended up fairly close, but it still was not that good. The red line is we went through and hand thinned to try to bring down the gold line to the black line for those fruits that were above it. So if we did hand thinning correctly, we should not have ever reduced crop load on the ones that were under the optimum, but we should have made the gold line come down closer to the black line, with the red line being the result. But you can see that by just focusing on hand thinning, we ended up with a number of trees that had too low of a crop because the chemical thinning over-thinned them. And some trees still ended up with a few more fruits than we wanted because the hand thinning was not perfect. And humans make mistakes when we tell them, take off 50 apples from that tree. They might take off too many or too few. So that part isn't perfect, but it still illustrates the problem of the variability down the row and why we need georeferencing of every tree. I guess I did put in the Hudson Valley data. This is the Hudson Valley plot where most trees were above the optimum, which is the black line. The gold line showed many, many trees above this optimum space. The hand thinning resulted in the red line, which was closer to the black line, but still there were some trees we didn't thin off enough, and a few that we thinned too many of. If you look right here at these trees, say 43 or 4 or 5, they should have been up at the black line, and we thinned them down to the red line. And then these trees around 62, we should have thinned to the black line, and they ended up with more fruits than we should have. So these are some initial efforts at trying to take this last step of precision hand thinning. Again, I hope that we could come up with a system so that the hand thinning people on the platform with an iPad in front of them would have this sort of information as they face a tree. It would say remove 20 apples from this tree. The next tree, it might say remove 30. A previous one might say remove 40. Then we rely on the human worker to follow the instructions, but it certainly would allow us to than just treating all the trees uniformly. The last thing I'll mention is just the part that I think has been most interesting to most of you commercial companies, and that is using computer vision to predict harvest. And that's not been a focus of mine. It's because predicting harvest is useful, but there's not a lot of money in it for the grower. It's very useful to the packing company to know how many bins they're going to expect and the fruit size. And it's very helpful to the grower to organize labor. And so that part's all understood. But in terms of really making a difference on the crop value, you don't really do much after this. And so you're just estimating the final result. We would like to be able to do that on July 1 and August 1. And so this would require computer vision to count fruitlets and measure size before harvest at least 2 times to predict yield. And this is some data that we did over the last several years. I believe this was all done with Pometa system, in which we harvested the tree and we predicted the number of fruits per tree. And you can see that when fruit number per tree was between about 25 and about 100, we were pretty accurate. But when fruit numbers exceeded 200, we weren't that accurate. And that's probably because of the hidden occlusion, the problem with when there's a lot of fruit on the tree. So I want to summarize this part of the presentation and the discussion with what we would love to see. This is our wish list of things we hope companies working in this space will work to achieve. First, we would love to have counts of dormant buds with each tree georeferenced. Number 2, we have to measure something on the tree that will be a suitable denominator to calculate what's the optimum bud number and what's the optimum fruit number later. And thirdly, we have to have a method to communicate that number for tree to the human worker so that he can prune trees more severely or less severely to leave a proper number of buds on the tree, because leaving too many buds on the tree always results in problems with too many fruits at the end. Once we progress towards bloom, we need the ability to count flower numbers per tree at bloom. This can start as early as pink. We need to have then estimates of how many flowers are open on a daily basis to start the pollen tube growth model. And then these flower counts were very essential to guide the smart sprayers for variable rate blossom spraying. We'd love to be able to count fruitlets after blossom thinning to guide chemical thinning, But equally and probably more important are digital measurements of fruit size so that we can run the fruit growth rate model using easy to acquire measurements without manual measurements with a caliper. That will guide chemical thinning. We then need to count fruitlets before hand thinning, and we need a method to calculate the denominator to calculate the optimum number. And that denominator probably has to be measured earlier in the season, because when you get to this point, it's hard to see the trunk. It's hard to see each branch's diameter, whatever method you use. Therefore, we think that you have to be able to measure these, whatever denominator we use, earlier in the season. Then we need a method. I like the iPad method to communicate the needs for each tree to the human workers. And then lastly, we need to count fruits and measure fruit size to predict yield and fruit size. So with that, that ends my presentation of what is the wish list that we in the project would love to see from each of the companies. I hope it's not too much to sort of get your mind around. I don't think any company is able to do it all right now. And I want to just say up front, I'm extremely appreciative of all of you and your companies working to help growers achieve what we need to get done for precision crop load management. But I hope that I've stimulated you to push beyond where you currently are. So with that, before I take questions or we have discussion, I want to call on a couple of people that are in the project, the engineering group from the universities, from Cornell and Penn State, to give us a short presentation on stuff that they've done that US companies might find useful if you want to work with them to achieve some of what I've talked about. So first, I'd like to call on Yu Jiang from Cornell to talk about his efforts to image trees.